Assalamualaikum warahmatullahi wabarakatuh. So for today we are from group 9 and we're going to present the details about our applications of drags. So for our title for today is drag force of container. My name is Faiz bin Nasser and my matrix number is 210158 and I'm going to introduce my friends over here.
Hello everyone, my name is Mohd Azim bin Resyidi and my metric number 211997.
Alright, Idzlan, next slide please. Okay, my name is Hisyam bin Azmi with metric number 213222.
My name is Khushaini bin Kamaruzaman, my metric number 213141.
And my name is Idzlan bin Azmi, metric number 212655.
Thank you everyone for a wonderful introduction. So I'm going to explain a little bit about introduction. So for the introduction of our application, which is the ships of container, the drag is the force that opposes the forward motion of an object in a fluid. So for our case of application, in this case, a container ship, the drag force is created by the resistance of the water against the ship's hull. The ship hull is obviously the bottom part of the ship that contain the total gravity of high to resist, which resists all the wave from the ocean, and hence which results in a decrease in the ship's speed and increase the power required to maintain its movement. So for the next slide, I'm going to pass my presentation to my friend.
Alright, for the theoretical, first is for the drag coefficient. The drag force on a container ship model depends on its shape, size and orientation with respect to the fluid flow. The drag coefficient is a dimensionless quantity that characterizes the shape-dependent drag on the model. It can be determined experimentally or through computational simulation, and it relates the drag force to the reference area of the model and the dynamic pressure, which is 1 over 2 rho v the power of 2 of the fluid, where the rho is the density of the fluid and v is the velocity of the fluid relative to the model. The drag force can be expressed as F drag equal to 1 over 2 rho A v the power of 2. The second one is the flow regimes. The flow around the container ship model can vary from laminar to turbulent depending on factors such as the ship size, speed and shape, as well as the properties of the fluid. The flow regime affect the drag force, with turbulent flow generally resulting in higher drag compared to laminar flow. Next slide please. Okay, so for the third is Reynolds number. The Reynolds number is a dimensionless parameter that describes the relative importance of the inertial forces to viscous forces in the fluid flow. It is calculated as a Reynolds number equal to rho VL over the efficiency, where L is a characteristic length of the model, such as the length of the ship, and the efficiency is the dynamic viscosity of the fluid. The Reynolds number can help determine the flow regime around the model and the corresponding drag force with different drag coefficient applicable to laminar and turbulent flow regimes. And the last one is additional factors. The theoretical understanding of drag force on a container ship model may also take into account other factors such as the effect of appendage, such as rudders, propellers, and other hydrodynamic features of the model, as well as the effects of waves, current, and other environmental conditions. Okay, so the next I will pass to the other group members.
Thank you, Azrul. So next I will explain or talk about application of drag force. So there are four applications that include in the drag force. So actually the journal that we discussed have the numerical simulation of drag force on a container ship hull in various operating conditions. So to conduct this research, the authors use computational fluid dynamic (CFD) simulation to model the flow of water around the ship hull and calculate the drag force. So there are considered several operating conditions, including different states, sea states, and loading condition. So they found that the drag force on the ship hull was influenced by a variety of factors. The drag force on the ship hull was influenced by a variety of factors such as the shape of the hull, the presence of appendix like rudders and propellers, and the interaction between the ship and the surrounding water. So one of the key findings of the study was the shape of the ship hull had a significant impact on the drag force. Specifically, they have found that the use of a bulbous bow and a stern bulb will reduce the drag force by up to 20% compared to a standard hull design. So the study also highlight the importance of the consideration, the effects of wave and sea currents on the drag force. The authors found that the drag force increased significantly in rough seas and when the ship was traveling against the current. So overall, the study provides valuable insight into the factors that influence drag force on container ship and how ship design and operating condition can be optimized to reduce drag force and improve efficiency. So I will pass up to next presenter. Thank you.
Okay, thank you, Azim. So now the drag force and the lift force. The drag force and lift force are both important factors that affect a container ship's motion through the water. The drag force is caused by the friction between the ship and hull and the water and acts in opposite direction of the ship's motion. This force increases with the speed of the ship and is affected by several factors such as I said, the shape and the size of the hull, the density, viscosity of the water, and the surface roughness of the hull. And the drag force can significantly impact a ship's speed and fuel efficiency, making it an essential consideration in the design and operation of container ships. So the lift force, on the other hand, acts perpendicular to the drag force and helps to lift the ship out of the water. This force is created by the pressure differences between the top and the bottom of the ship, which is caused by the shape of the hull and the speed of the ship. The lift force can be maximized by designing the streamlined hull, the reduced wave resistance and turbulence. However, if the lift force becomes too strong, it can cause the ship to rise out of the water and become unstable, which is why engineers must carefully balance the shape and the size of the hull, maintain stability and control. So in general, both of the drag and force and the lift force are important consideration in the design and operation of container ships. Engineers must balance these forces to ensure the ship can move efficiently through the water while maintaining stability and control. This may improve optimizing the shape and size of the hull using advanced propulsion system to reduce energy consumption and accounting for factors such as cargo weight or weather condition. By carefully considering these factors, container ships can be designed to operate efficiency and safety in variety of conditions. So I will pass to the next presenter.
Okay, so thank you, Idzlan. Now I will continue with the next topic, which is the parameters mechanism that needs to consider in order to find the hydrodynamic drag force. So essentially, the hydrodynamic drag force experienced by the container ship is influenced by several parameters. There are 6 parameters that I am going to explain. The first one is geometric shape of the ship. The design ship should consider a few things, including its length, beam, draft, and also form. For example, a streamlined hull design can reduce drag and improve the ship's performance. The bow shape and stern shape also play a significant role in reducing drag and improving the ship's efficiency. The second one is the speed of the ship through the water. As the ship's speed increases, the drag force also increases due to the increased resistance from the water. Third parameter is the ship size and its weight, where the larger and heavier ships will generally experience greater drag force. The fourth one is water depth, which influence the formation of waves and the associated wave resistance. Then, the fifth one, water density and viscosity. So the viscosity of the water, which is influenced by its temperature and salinity, can impact the drag force. Besides, every ocean has different value of water density that should be considered too. And the last one is turbulence and wave, which the presence of turbulence and wave in the water greatly impact the drag force that experienced by the ship. also can be called as a C condition that we are looking for actually, including the wave height, wave period, and also its current velocity. So, to sum up, all of the parameters that should be considered actually have the the relationship between each of them. So that's all from me. I will pass to Faiz for conclusion.
Thank you guys for a very amazing explanation from each of the parts for our presentation. So today I'm going to wrap up and give a very compact and simplified conclusion. So in conclusion, force do give significant impact to our overall daily utilities, especially for our research application that we are studied today, which is a ship container. By understanding the drag force of a container ships, we can essentially ensuring the safety and efficiency of marine transportation and thus can bring benefits such as minimizing drag, shipping companies can save fuel, reduce emissions, increase the speed and also capacity of their vessels, and lastly, making marine transportation more cost effective and sustainable. So I think we have already explained and give a very good explanation for our presentation today. We can wrap up for our presentation and thank you very much. That's all from us. Thank you.
Thank you.
Thank you, everyone.